Science friends. Today we are going to be talking more about the water molecule and about properties of water. So these properties of water, I actually do a lesson on this in AP Biology. They're really important as you get into biological systems because cells and living things are made up of so much water. And so you will see these properties of water come back again next year, and especially I know for sure if you take AP Bio with me next year, which I hope you all will. But water, as we discussed previously, is a highly polar molecule. So it's got that electronegative oxygen and the electropositive hydrogen. That means that the electrons are unequally shared. The oxygen's pulling on those electrons harder because it's more electronegative. And so they kind of get pulled away from the hydrogen toward the oxygen, making the oxygen more electronegative and giving it a partial negative charge, and the hydrogen a partial positive charge. And so, as we discussed, remember this is a covalent bond that holds that oxygen and that hydrogen together. Specifically, it's a polar covalent bond because it has a difference in electronegativity between oxygen and hydrogen is greater than 0.4, and because those electrons are shared unequally, as we just mentioned. So that is an intramolecular force. It's holding that water molecule together. So this one here is a hydrogen bond, and that is an intermolecular force that holds multiple water molecules together. And so they're being attracted both by those hydrogen bonds. The attraction between the partial positive charge of the hydrogen and the partial negative charge of the oxygen. And you'll see that on each one, the way they orient themselves, the positive of the hydrogen connected with the negative of the oxygen. Okay, and that shows that. Okay, so the water molecules are attracted to each other by hydrogen bonds. So you're going to do a lab today about surface tension. So what is surface tension? Well, because water forms these hydrogen bonds, it has a high surface tension. So a surface tension is like a skin that the water forms on its surface. If you've ever looked out at a lake or a puddle of water, sometimes you'll see insects be able to float on that or be able to walk on top of water. And they can do that because of that surface tension. Not all liquids would they be able to walk on top. Yes, it's because they're light, but more importantly, it's because they don't break that surface tension. And that surface tension is held together by those hydrogen bonds, those attractions between the negative oxygen and the positive hydrogen. So it's an inward force or pull that tends to minimize the surface area of a liquid. So remember, the surface area of a liquid or the surface area of anything is how much space it takes up. Let's take for an example, if you were to have a dropper full of oil and a dropper full of water, and you were to squirt drops of oil and drops of water out, and then measure the diameter of your puddle, so to speak. If you had done equal drops of oil and equal drops of water, your oil puddle would be bigger. It would have a larger surface area than the water because oil is nonpolar. So it doesn't have those hydrogen bonds, and it doesn't have that surface tension that kind of sucks it all up together, okay? Water, on the other hand, has these hydrogen bonds that kind of pull the molecules together, squeeze them in tight, gives them a hug from the inside. And so it minimizes the surface tension. So your puddle of water would be smaller in size than your puddle of oil for the same number of drops, just because of the ability of water to hydrogen bond because of its polar nature, okay? So that's what surface tension is. So some substances are called surfactants, and they reduce the surface tension right here, reduce the surface tension by disrupting the hydrogen bonds, which is what you read here. They interfere with those hydrogen bonds. So basically they kind of break these bonds down and they reduce the surface tension. So some examples of that you see here is soap and detergent. Generally things that are going to feel slippery are going to reduce the surface tension. Those slippery things are going to be non-polar. Now, we talk about this a lot again in biology, and I know I keep referencing biology, but you're all going to take biology, whether with me or Miss McLean or Mr. Bartley or somebody next year, you're all going to take biology. And so I'm just kind of previewing that into that here. But this becomes really important. Lipids are a class of molecule that we talk a lot about in biology, and they are non-polar. They're very slippery feeling. Oils, waxes, things that have that slimy feel are going to reduce the surface tension. And so in your lab today, you're going to put drops of water on a penny, plain water, and then soapy water. And you're going to see how adding just a drop of soap is going to affect the number of drops of water that you can get on that penny, okay? Because that soap is going to act as a surfactant to reduce that surface tension. All right. Now, the next thing, water has a low vapor pressure. It has a high heat of vaporization. And so what that means is it takes a lot of heat to add to water to make it turn into a vapor, to evaporate it, essentially. It takes a lot of heat to evaporate water. And so remember, molecules are constantly moving. Atoms and molecules, they never stop. Even in their frozen state, even if they're a solid, they're still vibrating. They're just vibrating in space, okay? If they're a liquid, they're sliding past one another. They're, weaving in and out and, kind of like somebody weaving in and out of traffic is how I think of it. And if they are a gas, then they're just bouncing off of erratically, just throwing a ball inside of a closed room and letting it just bounce and go, and it's never going to be stopped by friction or wind resistance or anything like that. So water has a high heat of vaporization, means it takes a lot of energy to make it evaporate. It also has a low vapor pressure. And so what that means is the pressure that's above a liquid in a sealed container due to the collisions that are happening. So this is our sealed container, okay? This is our open container. And so these little blue dots are our molecules, our water molecules. So over here on the right in this sealed container, these water molecules are just going to be bouncing off everywhere. And that's going to give that a high pressure, okay? Versus over here, they don't have anything to hold them in. And so they're going to be able to evaporate. And that gives them a low pressure. But relatively, water has a low vapor pressure. Because it has that high heat of vaporization, it takes a lot of energy to make it evaporate. And so because it doesn't evaporate easily, it's going to generally have a low vapor pressure in a sealed container. And again, that's because of those hydrogen molecules. That's because of those molecules that are holding the water together and not allowing it to escape. Now, when water evaporates, right? That means liquid in evaporation, liquid turns into a gas. So in a solid, these water molecules would be packed like in ice. These water molecules would be packed in tight here. And I'm just drawing them as one if you want to draw the, the extra oxygens and hydrogens on there, whatever. But they would be packed in tightly. And so the bonds, the hydrogen bonds that hold them together are very close. They're not spread out. That would be in a solid. In a liquid, remember the molecules are going to look more like this. They're a little bit more spread out. They are, but they're still being held together by those hydrogen bonds, okay? Now, if we had a gas, the molecules are going to be, even more spread out. And so it's going to put a lot of strain on those hydrogen bonds to be able to hold them together. And so at that point, when the hydrogen bonds can no longer hold them together, that's when you're going to hit that vapor pressure, that point of evaporation where the liquid is going to turn to a gas. But again, that's a very high temperature, okay? So that's all I've got for you today. You'll go ahead and complete that surface tension lab, and then tomorrow we will talk about specific heat. Okay? Y'all have a great day.